In this example, we're going to look at number 4 from section 4M. Asks us to find the greatest and least values of the function in the interval -3 to 3. You should already be pretty familiar with what this graph looks like. It is a cubic function, it has a negative leading coefficient, and it crosses the y-axis at 4. You'd be doing something like this. I don't know whether the maximums or the minimums are like left or right of the y-axis, so I'm not going to put any axes on here yet. We're only looking at like a shortened area. We're only going from -3 to 3. So it might be the case that those are the absolute maximum and absolute minimum that the graph reaches, but maybe it is more of this situation. So the endpoints are lower than those extremum on the inside. We will need to find the y values to know which of those cases it is. Let's go ahead and start with the y value of the endpoint. I think this entire exercise is intended to be done without a calculator, although it's going to get very tedious. We have 4 minus 15 minus 9 plus 27, which is -16 plus 4 is -12, or -16. So it's 4 minus 15 is -11, minus 9 is -20, plus 27 is 7. And then we want to find the other endpoint, so I have 4 plus 15 minus 9 minus 27. So 4 plus 15 is 19, minus 9 is 10, minus 27 is -17. To find the interior maximum, we're going to use the first derivative. So I take the first derivative. I'm going to write this in descending order rather than ascending like they have it here, because it's the way I'm used to seeing it, and I can wrap my brain around it a little bit more easily. So the first derivative is a quadratic function, and we should find where the zeros are. I can see here that this factors, because I already can see that -3 times 5 is -15, and -5 plus 3 makes -2. To explain that a little bit more, I take the leading coefficient and the constant and I multiply them. And then I look for two values that multiply to be this, but add to be this middle coefficient here, which means I can split the middle coefficients into -5x and +3x. Doesn't matter what order you put those in. You could have put them in the other order just now. It's going to lead to the same answer finally in the end. So -x, so this becomes 3x plus 5. They don't have a common factor, so 3x plus 5. And now I have -x plus 1 and 3x plus 5. So when this equals 0, x is going to be 1 or -5/3. And as I mentioned before, we know the graph looks like this. So this will be when the x is -5/3, and this will be when the x is 1. So potentially that is our max or our minimum. So let's be a little more serious about it and consider what the first derivative looks like. So this is a graph of f prime. I know it crosses at -5/3, and it crosses at 1, and I know it's concave down. This is definitely not what the graph looks like, but I only care about the sign, like the y coordinate, whether it's positive or negative. So it's a negative down here, it's positive in between, which means my graph, my original graph, from -3 to 3, it's decreasing, then it's increasing, and it's decreasing. So it's decreasing, increasing, decreasing. So this is a local minimum, and this is a local maximum. But they've asked us to find the greatest and least values. So I need to compare it with these endpoints. I'll need to calculate the value at each of those locations. So the question is, when I plug this x into my function, will I get a number that's smaller than -17? Find out. So f of -5/3 equals 4 minus 25/3 minus 25 ninths plus 125 over 27. Adding these without a calculator is going to be annoying. This would be negative 67 over 27. I don't know the exact value of that, but it's much smaller than negative 17. In fact, you can't even get to 3. So my absolute least value that this graph reaches is negative 17. So let's consider the maximum. So f of 1, a much easier value to plug in. 4 plus 5 minus 1 is 7. So it's at the same place. The greatest value that the function reaches is at 7, but it does so twice. This question is from section 4M. It's number 4. It asks us to find the least and greatest values of a function on a closed interval. So because the interval is closed, I need to check both endpoints and then find any local maximum or minimum on the inside. So the function that I'm given is f of x equals 4, 5x minus x squared minus x cubed. We should already be pretty familiar with the way that cubic functions look, and if the leading coefficient, like the coefficient in front of the x cubed term, is negative, this graph is doing something like this. We are certainly going to be looking for the possibility that there is both a local minimum and a local maximum, and then depending on what the endpoints do, maybe negative 3 leads us way up here and way down here. So like those endpoints will be the actual extremum. Let's go ahead and find the endpoints before we get started. So when we're at negative 3, 4 minus 15 plus 9. So negative 3 cubed is negative 27, but then there's a negative on there, so that's plus 27. We could calculate this by hand, but that seems a non-wise idea. Just use a calculator here. 25. And the other endpoints is for plus 15 So let's consider the endpoints. I have f of negative 3, which is 4 minus 15 minus 9 plus 27, because it's a minus minus, which equals, let's go to the calculator. I think it's safer and perhaps a little faster. And I want to find the other endpoint as well. So it's 4 plus 15, still minus 9, and this time it'll be minus 27. That's negative 7. Or close. Negative 17. So it may turn out that those are the absolute maximum and the absolute minimum that this graph reaches on that interval, but we should double check by using the first derivative. So f prime of x is 5 minus 2x minus 3x squared. We find our extremum by setting the first derivative equal to 0. I'm going to write this the other way around. It's easier for me to factor when I have them in descending order of exponents. It doesn't really make a difference, but my brain wraps a bit better in the standard order. Okay, so this factors. I'm going to go ahead and factor it. I know that negative 3 and 5 make negative 15, so I'm going to have a negative 5 and a positive 3. We'll have negative 3x times x minus 1 minus 5 times x minus 1. So my critical points, my possible extremum, are at x equals -5/3 and +1. Because I know the cubic function looks like, I know this one on the left will be the one that's the minimum, and the one on the right is the one that's the maximum, because it looks like this. We should probably double check. I think the easiest way in this moment to double check is let's just look at the graph of the derivative so we can consider our test points. So the derivative is a quadratic with a leading coefficient of -3, and I know where it crosses 0. So it crosses here at -5/3 and it crosses here at 1. And it looks something like this. And what I care about with the first derivative are the signs. So it's negative and then positive and then negative. I mean like the sign of the y coordinate, which means in my first derivative test, my function is decreasing, then increasing, then decreasing. So decreasing, increasing, decreasing, which makes this a minimum and this a maximum. But is that minimum lower than this absolute minimum we have here at our endpoints? But is this minimum lower than the minimum of the endpoints? We need to find that out. So let's find out what is f of -5/3. I'm not even going to attempt to do this by hand. You could. I certainly also could, but as far as time is concerned, don't know that's the best use of my time. I have 4 plus 5 times -thirds, thirds, thirds. Oh, I lost my negatives. Not that it mattered on the square. It will matter quite a lot here. We'll check. 2.48, so this is approximately -2.